Okay, everybody. I hope everybody's doing pretty well today. Today, we're going to take a look at techniques of integration. And so this is going to be sort of one part and several parts or sections that we get into involving different techniques of integration. Um, so the first thing I'm going to do today is that we're going to look at integration by substitution. I'm just going to take an overview of that. But now we're going to do this with a bit of a twist. In an earlier video, I've already talked about the substitution method, and we've looked at some examples of using the substitution method, but that was on a basic level. In this chapter, we're going to look at using the substitution method in some cases, and also some other tips and tricks for integrating certain functions. These don't require any new techniques, but many of these problems will require that we do some things that we might not normally think of doing. And so the purpose of the video is to kind of show you these problems to hopefully sort of expand your thinking and expand the ways that you can approach some of the integral problems. So we're going to take a look at several examples in this video. So the first one we have is the integral the integral of e to the 2x over e to the 2x minus 4 times e to the negative x dx. Now, in this example, we're going to look at how we can use a little bit of manipulation before we apply substitution. When we look at this problem on the surface, what we see is that we see a lot of e to the x functions. Now, one real nice thing about e to the x and the substitution method is that we know that e to the x is its own derivative and its own antiderivative too. One inclination that we might have is to let u equal e to the x or in this case, e to the 2x, since that's what we see most prominently. But now, of course, this doesn't really work for us too well because we have that denominator, and the denominator is the more complicated term here. So we might say, well, why don't we let u equal e to the 2x minus 4e to the negative x? Now, of course, the problem that we run into here is that du is not going to be so cut and dried. It's going to be 2e to the 2x plus 4e to the negative x, which we don't see in the numerator. So on the surface, using substitution might seem as if it's fruitless. However, if we make one adjustment to the integral, to the expression itself, we can actually come to a point where we can use substitution. So what's the trick here? Here, the trick is going to be to take the expression and multiply the top and the bottom by e to the x power. Now, why are we doing that? Well, the reason why we want to do that is because the e to the x power will cancel out e to the negative x, and it'll create a constant term there. So let's take a look at that, and we'll see how this works out. So if we do that, then our integral becomes e to the 3x over e to the 3x minus 4 dx. Well, the convenience here is that now, if we use substitution, letting u be the denominator, e to the 3x minus 4, then its derivative, du, would simply be e to the 3x, or I should say 3e to the 3x dx. And we have that e to the 3x factor in the numerator. So here, things work out a whole lot better for the substitution method. But you note here that we did some manipulation to the expression in order for us to use substitution in a very straightforward way. All right, so rewriting this integral in terms of u, it simply gives us, now with the 3, we need to multiply and divide out by 3. And so we'll have the integral of 1/3 du over u, okay, which we know is the natural log of the absolute value of u plus c. And so now putting it back in terms of x, u being the denominator, e to the 3x minus 4, we'll have 1/3 times the natural log of the absolute value of e to the 3x minus 4 plus c. Okay, so one trick that we see here is that in order to use the substitution method in a way that works for us, we needed to multiply the top and the bottom by an expression that allowed us to use substitution. All right, so let's take a look at another example. All right, so in this example, we're going to deal with the notion of splitting fractions. Now, this is something that you may have done in previous problems, but once again, it's a technique that's oftentimes used, especially for problems like this, where one method or the other doesn't necessarily work. So, for example, here, once again, using substitution directly doesn't really profit us here, because if we let u, for example, equal the denominator, not the whole denominator, but just 4 minus x squared, du ends up being negative 2x dx. And although we have a 3x term here that we could work with, and that could work, that extra term of +1 kind of throws a wrench in all of that. Because when we want to convert this in terms of u, that additional term of 1 we have to account for. So what we can do here to kind of make things work out in our favor is that we can actually split the fraction up. That is to say, we rewrite the integral in two parts. So we have 3x over the square root of 4 minus x squared plus 1 over the square root of 4 minus x squared. So this way we can, excuse me, this way we can deal with each term separately. That's 4 minus x squared. And that second term, we should recognize that that's going to be one of the inverse trig functions. So that's going to be convenient for us. So now let's go ahead, work with each of these individually. So let's do the first one. So the integral of 3x over the square root 4 minus x squared dx. All right, so here we let u equal 4 minus x squared. Its derivative du will be negative 2x dx. All right, so now in this problem, we need the -2 factor, so we can multiply and divide out by -2 to get that factor. The 3 in the 3x will bring out in front, so that in terms of u, this becomes -3/2 times the integral of du over the square root of u. Now, of course, the square root of u on the denominator is just equivalent to u to the negative 1/2 power. So if we integrate that, we'll have negative 3/2 times 2 over 1 times u to the 1/2 power. So it's u to the 1/2 power divided by 1/2. Dividing by 1/2 is the same as multiplying by 2. So simplifying this, the 2's will cancel out. This will be negative 3. Now let's put it back in terms of x now. So we'll have negative 3 times u to the 1/2 power. U is 4 minus x squared. So it's going to be negative 3 times the square root of 4 minus x squared. All right, so that's going to be the first part of our problem here. Now for the second part, we have 1 over 4 minus x squared. Or 1 over the square root of 4 minus x squared dx. So now if you look at this, if you recognize, has the same form as one of the inverse trigonometric functions, namely the inverse sine. So the general formula here for the inverse sine, if you have dx over the square root of a squared minus x squared, that's going to be equal to the inverse sine of x over a plus c. And so in this case, our a value, a squared is going to represent 4, so a is going to be equal to 2. And so we can just go straight to the result here, which will be the inverse sine of x over 2 plus c. All right, so that's the second term. So now putting this all together, our answer, our final result here will be negative 3 times the square root of 4 minus x squared plus inverse sine of x over 2 plus c. All right, so the key thing here is that you got this fraction and you got multiple terms. The thing that you want to look for here, substitution can be something that really works in our favor. But in order for us to use substitution, we may have to do some separation of the terms, breaking them up in such a way, and maybe dealing with them one at a time. All right, now you may not have to do this with all problems, but once again, we're just looking at some tips, some tricks, some ideas that we can use to help us evaluate several of these different types of integrals. All right, so let's take a look at another example. Now, one thing you'll probably notice is that a lot of these integrals that I'm showing you are fractions or rational expressions or pseudo-rational expressions. And it's kind of important to note that rational expressions can be a bit of a challenge because there are so many different ways that you get rational expressions when you differentiate a function. Obviously, the derivative of a rational function is going to more than likely give you a rational function. But also consider that the natural log function. If you take the natural log of x, its derivative is 1 over x, a rational function. The inverse trig functions, their derivatives are rational functions. So rational functions, when you see a rational function as an integral, it has the potential to branch out into so many different possibilities. It could be a rational function, it could be a natural log, it could be an inverse trig functions, it could be a combination of all of those. And so that's one reason why you see when we deal with these rational functions, we have to take some care, and also we may have to do some things with the problem in order to get it into a recognizable form that we can use, that we can evaluate the integral with. All right, so in the third example, we have the integral of x to the fourth minus 6 over x squared plus 4 dx. Now here, obviously, you can kind of see in this instance where a separation of the fraction may be warranted, because at least with having the 6 over x squared plus 4, that kind of reminds us of the inverse tangent. But then you have that x to the fourth power. That's not something that we could easily use substitution for in this problem. So one particular method that we can do here, especially if we have polynomials, and particularly in the case where the numerator has an equal or a higher degree than the denominator, is to divide the polynomials. Now, one thing I also want to mention is that the methods that I'm showing you are not the only methods that you could use for solving some of these integrals. There may be some other alternate method that you could use to evaluate some of the integrals that I'm showing you. However, the idea here is just sort of to open your eyes and to open your mind to different things that we can do in order to help us evaluate these integrals. And we're not doing anything really all that new. This isn't a new technique of integration. All we're basically doing is applying some algebraic methods and then using substitution, which we've already learned, in order to evaluate these integrals. So let's look at the next example. We have x to the fourth minus 6 over x squared plus 4. And so here we're going to divide the polynomials. So let's do the polynomial division. And we'll do that off to the side here. So we're going to take x squared plus 4 and divide that into x to the fourth minus 6. Now you've got a lot of missing terms here in our dividend. So we're going to fill in some of the gaps here because we'll need those. So we'll put in 0x cubed, 0x squared, 0x, and then our last term, which was 6. Now, we may not need all of these, but we want to make sure that we don't make the mistake of combining terms that are not like. All right, so x squared into x to the fourth, that'll be x squared times. So then you take x squared times x squared plus 4. So that'll be x squared times x squared is x to the fourth. X squared times 4, that's 4x squared. And note, I'm putting it underneath the x squared term. And then we subtract that quantity. So x to the fourth will cancel out. 0 minus 4, that's going to give us negative 4x squared. All right, and so we bring down the next term. Okay, and I'm bringing down the third term because we'll need to. So x squared into negative 4x squared, that's going to be minus 4. Then take negative 4 times x squared plus 4. So it'll be negative 4x squared. Negative 4 times 4 is negative 16. And then we subtract that quantity. So negative 4x squared minus negative 4x squared cancels out. Negative 6 minus negative 16, that's going to be equal to positive 10. All right, so the 10, that's going to be the remainder. And so as you know, we put the remainder over the divisor. So we'll have x squared minus 4 plus 10 over x squared plus 4. So now rewriting our integral, now this is the quotient and the remainder from the division. So this integral can be rewritten using this entire expression here. So this will be equal to the integral of x squared minus 4 plus 10 over x squared plus 4 dx. And so now here, the integration is very simple because you have just a polynomial in the third term, 10 over x squared plus 4, that has the form of the inverse tangent. So evaluating that, will give us x cubed over 3 minus 4x plus 10 times, now this is x squared plus 4, so it's going to give us 1/2 times the inverse tangent of x over 2 plus c. The 10 and the 1/2 we can multiply together. So we get x cubed over 3 minus 4x plus 5 times the inverse tangent of x over 2 plus c. All right, so now the last problem we're going to look at for this section is the method of completing the square, and we have yet another rational function. So here we have 7 over x squared plus 6x plus 25. Now this one's particularly tricky because we can obviously see that using the substitution method in the simplest sense isn't going to work for us in this case. Letting u be the denominator, x squared plus 6x plus 25 would yield a derivative, a du of 2x plus 6, and we've got nothing like that in the numerator, okay? So now how do we handle this? What do we do with this problem? Well, this is where we're going to be using a bit of a trick called completing the square. Now, this is almost kind of a niche method here because you almost have to know what to look for in cases like this. So now, what is it that I see in the problem that tells me that completing the square is a possibility for us here? Well, it's with the denominator, x squared plus 6x plus 25. Now, seeing as how just using substitution directly wasn't going to give us what we wanted, I look at the denominator and I notice that this denominator is an irreducible quadratic. So in other words, what that means is that it's not factorable. Okay, so this is something that we can't factor over the rational numbers. So we can't, none of the factoring techniques for factoring quadratics or polynomials will work on our behalf here. And so we consider this to be irreducible. We could also say it's irreducible over the real numbers. But the key that it's not factorable is an important factor here. So what do we do with this? Well, I'm going to assume that you are familiar with the notion of completing the square and what that means. So if not, you can throw a comment in, throw a comment um, in the comment section and let me know. And if there's opportunity, perhaps I'll take some time and put a video together about completing the square. So in the denominator, we have x squared plus 6x plus 25. And so we're going to basically work with this expression to write it as a perfect square trinomial. All right, so now what do we do here? Well, we're going to push the 25, excuse me, we're going to push the 25 off to the side. All right, now it's not completely gone, we're just kind of moving it to the side. So now with completing the square, you want to find a number. You start with the quadratic and linear term, and you want to add a number to that expression that's going to make it a perfect square trinomial. That is to say, when you factor it out, it becomes some quantity squared. So if you recall, the trick is to look at the linear coefficient, which is 6. We take the 6, we divide it by 2. That gives us 3. And then we square the 3. That'll give us 9. All right, so that's how we complete the square. Take half the linear coefficient, and then you square the result. So half of 6 is 3, 3 squared is 9. So we're going to add 9 to this expression. Now, we want to keep the expression the same. So over with the 25 that we kind of pushed to the side, we're going to subtract the 9 back out. All right, so the purpose of that is to make sure that this is still an equivalent expression. All right, but I'm just grouping the terms a little bit differently. So now looking at the trinomial part here, x squared plus 6x plus 9, that factors, and it should be pretty easy to see that that's going to factor to give us x plus 3 quantity squared. Now, of course, that's why it's called completing the square, because we get something squared when we factor it out. Now, what about the stuff we pushed off to the side? Well, we can combine those two, 25 minus 9, that's going to give us 16. All right, and so now the completed square form of x squared plus 6x plus 25 is going to be equivalent to x plus 3 quantity squared plus 16. So now let's bring that back to our integral problem. So this integral will be equivalent to the integral of 7 over x plus 3 squared plus 16 dx. Now, by completing the square, we've done something that's really nice. If you look at the form of the integral now, this has the exact form of one of the inverse trig functions, namely the inverse tangent. All right, the general inverse tangent formula, if we have dx over u squared plus a squared, that's equal to 1 over a times the inverse tangent of u over a plus c. So that's the general formula here. So in this case, u is going to be x plus 3. We don't need it to be the entire denominator. Now, here, u being x plus 3, du is simply going to be dx. So that's all taken care of. All right, so there's no additional manipulation that we need here. Our a value, a squared is going to be 16. So a is going to be equal to 4. And so now, just follow the formula. Well, let's go ahead and write it in terms of u. So if we do that in terms of u, this will be 7 over u squared plus 16. 7's a constant, bring that out in front. So we have 7 times, and then we use our inverse tangent formula. So it'll be 1/4 times the inverse tangent of u over 4 plus c. And then finally putting it back in terms of x, we'll have 7/4 times the inverse tangent of x plus 3 over 4 plus c. All right, so that's our final result. All right, so now this is not a comprehensive list of all of the different types of integrals that you might see when you're working on the problems here, but this hopefully will give you an idea of some approaches that you can take when you're looking at some of these integrals where at first glance, simple substitution doesn't seem to work in your favor. All right, so take a look at these, rewatch the video, pay attention to the tricks that are being used. If you have your textbook, you can read through the book. There may be some other examples or methods that they present. Hopefully this was helpful. When we come back, I'm hoping to continue with our next part into the techniques of integration, where we talk about integration by parts. All right, so you guys have a good day, and I'll see you then.